Questions about anything? Well, today I'm going to discuss section 3.2, which is some basic facts about limits. I'll try to make it fun. Some of this stuff seems kind of routine, especially after freshman calculus. These are things that you have believed now for years and months. But now we're going to think about them from first principles. First concept I want to discuss is the idea of a bounded sequence. I mentioned one of my favorite bounded sequences, sine of n. Since pi is an irrational number, you can find rational numbers, p over q, which are approximately equal to n, pi rather. P over q is approximately pi, or pick anything you want. How about pi over 4? Okay, pi over 4 is irrational, because pi is. But you can find a rational number that's as close as you want, and then you get that maybe p is approximately q times pi over 4. And so sine of p would be approximately sine of q times pi over 4. Or if I made it be pi, for example, then I would have here q pi, and sine of q pi is 0. That means there's always sine of p's that are close to sine of an n that's close to 0. And you can make sine of n close to 1 if you want, and test it. Anyway, it's a wacky series that goes all over the place. That's what I'm trying to convince you. And sine of q pi equals 0. So for example, sine of n is never 0, but there's times when it gets close to 0. And in fact, you can make it get close to anything you want by playing this game. So this is just parenthetical. Anyway, it's a weird series because it goes all over the place. But at least it's bounded. So that's a fancy word that I'm going to tell you exactly what it means. Because we know that the sign is always between -1 and +1, less than or equal to, because sine of theta is less than or equal to 1 for all theta. Okay. So it might go all over the place, but at least it sticks between -1 and +1. A wilder example would be n times sine of n. That would go all over the place and get gigantic sometimes and get gigantic negative sometimes. Let's see. So I should define what it means to be bounded precisely. So a sequence xn, as n goes from 1 to infinity, is bounded sequence means there is a number m, a positive number. There is an m bigger than 0 such that the absolute value of every term is less than or equal to m. Some books might say less than m there, but our book says less than or equal to m. It gives you the same definition for all n. Okay. So for the case of sine of n, the bound is 1. But the bound could be something bigger. Well, this very simple theorem that you've probably heard before is that if a sequence converges, it has to be bounded. A convergent sequence must be bounded. And whenever I'm going to think about one of these things, the first thing I do is draw a picture to convince myself that it's true. So let's think. Let's suppose I have a convergent sequence, which means that I have xn converging to an L in L, of course, is a real number. It's not plus or minus infinity, because we haven't dealt with that case. So later. Okay, so if you think about our picture I drew for for convergence, the picture looked like this. Here was L, and then I made an epsilon I would choose, 1, 2, etc., 3 maybe, dot, dot, dot. And then I took an epsilon, L plus epsilon, and an L minus epsilon. So here's L plus epsilon, L minus epsilon. And then the definition of convergence meant that there's an n, so that eventually all the terms in the series sequence get squeezed into this tolerance. And so obviously the stuff that's stuck in that little band is nice and bounded. But in the beginning, I can't say anything about it. It could go wild and crazy. So I could have a gigantic negative thing for 1, a gigantic positive thing for 2. Who knows, maybe 3 falls in the band. But anyway, there might be some wild and crazy ones in the beginning that aren't stuck in that band, but at least there's only finitely many of them. And so I can just see the bound there. I look at, oh, this one is my biggest negative one, this one's my biggest positive one. I take their absolute values, and that would be the bound. Okay, so now that I understand it perfectly, in fact, I have to write down a mathematical demonstration of the fact. And you realize in that picture, I might as well take epsilon to be something like 1. And so every book you'll ever see says, okay, take epsilon equal to 1. So take epsilon equal to 1. I get an n such that xn minus the limit is less than 1. That's the epsilon. When n is bigger than equal to n. That's the definition of limits existing and being L. Okay, and now here's I can see in the picture what the bound is. But, you know, my L might be a negative number. And so I would have to draw a picture for a negative L too. And you can believe that that would look similar and be true, but I'd have to think about what my bound would be. Let's see, in this picture, my L is positive, and so my upper bound there of the top green dotted line would be L plus epsilon. Okay, but if my L was negative, then it would be L minus epsilon, absolute value of that. So I don't want to think of cases. So here's one of today's tricks. There's going to be 2 or 3 of them. Add and subtract something clever. add and subtract something clever, and use the triangle inequality. And it might be, there's two kinds of triangle inequalities, so it's either the less than or equal to or the greater than or equal to, depending on what you want to do. Obviously, when we want to get something less than epsilon or bounded, we're going to use the less than inequality in the triangle inequality. Okay, so using the trick for here, you think about it for a while. I want to get a bound on the x sub n. And I have a bound on x sub n minus L. So the clever trick is subtract L and add it back. That doesn't change anything. And now use the triangle inequality. That's less than or equal to xn minus L plus absolute L. And now I have that this is less than 1. This is less than 1 when n is bigger than or equal to capital N. And so then I get that this is less than or equal to 1 plus absolute L when n is bigger than or equal to n. I could see that from the picture, but I'd have to do cases where L's positive, L's negative, and it'd be kind of tedious to sit through. So that trick saves you some time. Questions about that trick? It's a good trick. I'm going to use it a couple times today. Let's see. So that's what I get. Oh, so now I've got the tail end bounded. The tail end of that sequence is nice and bounded by that thing. And so now the m I need would be the max of the wild and crazy ones in the beginning and then all the rest are bounded by 1 plus absolute L. That's my bound. And that's finite many things, so of course there's max. I want you to read this section carefully. I'm going to skip some of the really elementary and sort of tedious things. I'm only going to do what I consider to be the fun parts. Okay. And I'm considering this next thing to be a fun part. That the things you learn about in freshman calculus are correct. Namely, let's suppose that I have L sub n converges to L as n goes to infinity for letter equals x, y, z. Then the facts you learned in freshman calculus, namely that the sum of a limit, what did you learn? The limit of a sum is the sum of the limits. So, limit of xn plus yn equals the limit of x plus the limit of y, if those limits exist. So this says that that limit of those xn plus yn has a limit when the limits of xn and yn exist and are x plus y. So that's a part of the statement of the theorem. Part of the statement is this limit exists. Okay. And let's see, another one that's interesting is that the limit of a product exists. And is what you were told it was, namely the product of the limits. And a bigger one, let's see, this is kind of a dumb one. Limit of a constant times xn is the constant times the limit when c is a constant. That's kind of a no-brainer. More subtle one is that you can do the same thing with quotients, provided that you're not dividing by 0. That's going to be x over y, provided that y is not equal to 0. Y is equal to 0, of course, you're getting into thin ice. And you know, some of those early YNs might be 0, but eventually if they were going to something non-zero, they won't be 0 after a while. And then you'll be safe dividing by YN. But there might be some zeros in the beginning that you might have to come clean about. Nobody likes to divide by 0. Okay, so I'm going to prove number 1 just to show you one of today's tricks. I'm not going to prove all these things. So let's do number 1. Xn plus Yn, I want to show that that converges to x plus y. And so, of course, I write out what I'm looking for here. I want to make this small. Then I separate it into pieces. I put the x's together and the y's together. And then I do the triangle inequality, and this brings me to trick number 1 today, which is if you want to make something epsilon and you can pin it down into 2 things, make them both less than epsilon over 2. So I would make this one less than epsilon over 2, and this one less than epsilon over 2. This is the epsilon over 2 trick. Let's see, that one I can make less than epsilon over 2 when n is bigger than something. I'll call it n sub x. This one I can make bigger than epsilon over 2 when n is bigger than or equal to y sub n sub y, some other number. And so I can make that thing less than epsilon. Epsilon over 2 plus epsilon over 2 equals epsilon when n is bigger than or equal to the max of those 2 things. Check. So that's kind of a simple thing to think about using the definitions. Question? You could, and you'd get epsilon over 2, which is also less than epsilon. And if you had 10 things, you'd make each one be less than epsilon over 10. So, I mean, it's a trick. And it's maybe a compulsive OCD kind of trick. Because, you know, if I can make something be 100 times something small, then I make that small thing divide by 100, and I can, you know. So once you're comfortable with that trick, maybe you can stop doing this. If I get it to be pi less than pi epsilon, that's enough, because I could go back and change my epsilon to epsilon over pi. Anyway, the book is compulsive about this in the beginning, and it's a good thing to do for a while until you realize you don't have to do it every time. I think the product one is more fun and interesting, so number 2, the product one is I want to look at xn times yn and show that that gets close to x times y. And I have to do it in a precise, measurable way. Well, this is where my add and subtract trick comes in again. Add and subtract something clever. let's see, what's it going to be? We'll pick one thing. I think I'll pick the other thing. I'm going to pick minus x times yn. So the thing is, I can't do algebra and pull this part into two pieces just yet. I'd like to be able to pull out an xn minus yn. Or, yeah, I want to pull out an xn minus x. So I say, if I had that factored like that, I could factor out a yn times x minus x. That would be a good thing. So that feels like a good thing to deal with the first term. Well, if I subtract it, I would need to add it back. And then kind of something lucky happens. That's going to make me be able to deal with the second term. So now I've added and subtracted something clever. This is equal to this so far. This is less than or equal to, I'll take the first one, xn times yn minus x times yn, plus, and the second one would be x times yn minus x times y. And you realize, this is less than or equal to, I can factor out the yn from that first one. And I can factor out the x from the second one. Okay, so remember the first fact I showed you today is that if a sequence converges, then it's bounded. So I know that we know this is bounded by M, since yn converges. Okay, and xn converges. So I would want to make this term less than, well, let's see, epsilon over 2 is my usual thing, but I've got the stupid m in front. So I'll make it less than epsilon over 2m. Then my first term would be less than epsilon over 2m. So that would be true if n is bigger than or equal to, I'll call it n sub x. Okay, I'm getting somewhere now. And x, absolute x is just a number. So I don't have to worry about doing anything to it. It's there. I can't do anything to it. But I can make this one small. Let me think what I want. I want epsilon over 2, but that x is in front, so I'll take epsilon over 2x when n is bigger than or equal to some number, which I'll call n sub y. And so that's going to be less than a big fat epsilon. When n is bigger than or equal to the max of those two. Does anything bother you? Yeah.
The limit of x can be 0.
Yeah. What if x was there? If x was 0, then when I divide by x there, of course I'd be doing something insane. So that's the moment where you say, oops. Works when x is unequal to 0. What if x equals 0? What if x is equal to 0?
Do x and y instead?
Well, that would be one thing to do, maybe. But if x is 0, that term isn't there, so I don't have to worry about it. I don't have to estimate it. That works when, and the aha is, if x is equal to 0, then that term isn't even there, and I don't have to worry about it. So we're done. all the cases, those are two cases to do, x unequal to 0 and x equal to 0. Questions about that? Somehow I liked these arguments when I was first seeing them, and I kept a little notebook where I'd write them down carefully. That's probably shows that I was destined to go into this subject. I grew up in Wayne, Michigan, and that was before they were teaching calculus in high school. And I had a teacher who lent me her college calculus book when she got tired of trying to answer my questions. So that's why I became obsessed with these things. Okay, I'll skip the constant one because we've kind of seen the basic idea, but the quotient one is more interesting. So I'm thinking about the quotient one. I would have xn over yn, and I like to be lazy. I'd like to be able to use my previous thing and skip some heavier things. So if I were to write out xn minus over yn minus x over y and try to play around with algebra, it would get kind of messy. I wouldn't be surprised if I would succeed eventually, but it gets messy, and I'd like to reduce it to a previous case. So let's think about this case. I can write the quotient as xn times 1 over yn. Okay. So we're going to reduce the quotient case to the product case using a little related fact, kind of a lemma. 1 over yn goes to 1 over y, provided that y is unequal to 0. Okay, and that turns out to be not so hard. Let's think about it. Let's have 1 over yn minus 1 over y. I can multiply those, I can cross multiply and see that that's equal to y minus yn over yn times y minus yn over yn times y. And I want to show that I can make that small. Well, I can make the numerator small, and that y in the bottom is just a number, so I'd make it less than epsilon and think about it and make that epsilon on the top be epsilon times y, absolute y. But then I've got this stupid y sub n in the denominator. And the danger would be if the y sub n was 0. I'd be dividing by something small. But y is not equal to 0. So I'm going to draw a picture where y is positive. There's a positive y. The y-n's are approaching y. So there'd be some n out here. I'd put a narrow band here. Let's see, I would make my narrow band narrow enough so it doesn't get anywhere near 0. Any book you ever see is going to take it to be the halfway point. So this would be y over 2. This would be 3y over 2. And then my terms would be stuck between those two. etc. And those eventually would stay away from 0. Okay? And so you believe that eventually I can make those yn stay away from 0. And they won't mess up make it dividing by 0. Okay? Well, that picture convinced me that it's going to be true. And whenever you have to demonstrate something like this from inequalities, it's the triangle inequality you're going to use. And the picture gives you the idea about what exactly you need. Let's see. Let's think about it. Yeah, anytime you see a picture like that, if you see what you want, it's true. Those things are staying away from 0. And in fact, the distance they're staying away is y over 2. Okay? But I want this argument to work even when y is negative. So here's the sequence of things you need to do. I want it greater than or equal to inequality. Let's see. I guess, all right, so I'm going to have y minus, this is one of the triangle inequalities. This is less than or equal to y minus yn. And I'm making that be less than y over 2 in this picture. Okay, that's one of the consequences of the triangle inequality on the left, and that's from the picture on the right, the purple part. Okay, you look at that and say, oh, how am I going to get an estimate for yn out of that? Well, this inequality means that, okay, so what I have, y minus yn is less than absolute y over 2. Okay, and so that means that minus absolute y over 2 is less than something is less than plus absolute over 2. And now I can do a little algebra and see that, okay, minus 3 absolute y over 2 is less than minus yn is less than minus y over 2. And now I can take minus of that and reverse the inequalities and get 3y over 2 is greater than yn is greater than y over 2. And this is the one I want. That's the one I see from the picture. Okay, so whenever you see something from the picture, you can monkey around with triangle inequalities and get the fact that all those red dots are above the line y over 2. That was when y is positive. It's upside down when y is negative. And this string of inequalities is how you demonstrate it as a consequence of the triangle inequality. You only have to do it once, and then you believe it. Okay, so when I go back to estimating my thing here, back to, we have 1 over yn minus 1 over y equals y minus yn over yn times y. And I'll make, let's see, there's an n. We'll have yn greater or equal to y over 2 if n is greater or equal to I'll call it n1. Okay, so that's going to take care of that thing in the denominator. And so this is going to be less than y minus yn over y over 2 times y. And so I'll be done. That's just a number in the denominator. So I'll be done if y minus yn is less than that stuff times epsilon, which would be absolute y squared over 2, when n is greater or equal to n2. And then we would take, of course, the maximum of those two n's. Seems like a lot of technical stuff, but it follows from sort of easy concepts. If something's in a denominator, you need it to be bigger than something. If something's in a numerator, you want it to be less than something. And you can usually pick those things cleverly and make everything work. Okay, that's enough of that stuff. Questions about anything? Yeah.
Isn't like epsilon times the y squared? Can we just remove the absolute value from that? And square
Oh, you could, right. That'd make it look a little bit cleaner. Yeah. Let's do some easy examples now. Let's do an example. How about 5n minus 7 over 2n squared plus 3? Well, that looks like an infinity over infinity kind of thing. And we don't know anything about that yet. So you stare at that for a while. And in fact, you probably learned a trick in freshman calculus where you look for the biggest power. And they're the biggest powers too. And you multiply on the top and the bottom by 1 over the biggest power. N squared is the biggest power. And when you mess around with it, you would get 5 over n minus 7 over n squared on the top. And on the bottom, you'd get 2 plus 3 over n squared. And so let's see. Now we know some facts about, we know that 1 over n goes to 0. So let's see, what are all the facts I'm going to use here? We know that 1 over n goes to 0. And so, of course, 5 times 1 over n goes to 0. 5 times 1 over n tends to 5 times the limit of 1 over n equals 0. That's one of the things in the list, or the C. And we know that the difference of things goes to 0. Well, let's see. What do we know? 1 over n goes to 0, so 1 over n times 1 over n goes to 0. That would tend to 0 times 0 by the product rule, etc. And so you can see that this is going to go to 5 times 0 minus 7 times 0 squared over, oh, the quotient goes to 2 on the bottom. So that'd be 2 plus 3 times 0 squared. And of course, that's 0 over 2 equals 0. I'm using all the theorems in the thing above there. And it's important that 2 be not 0. So I can use the quotient rule. Anyway, after you do that once, you realize, okay, I don't have to say all the words anymore. I see it. Small minus small over 2 plus small is going to tend to small. That's what we said in freshman calculus. Now we're being more picky and careful about it. It's important to do that. Let's see. I guess I should talk about a few easy things at the end here after all this technical work. So here's some easy things. Oh, here's an easy one. If you have a sequence that goes to 0, as n goes to infinity, and a bounded sequence, then multiplying by a bounded sequence doesn't change the fact that the thing goes to 0. So the product would still go to 0. That's an easy fact. So that I kind of did that when I multiplied 1 over n by sine of n times minus 1 to the n. That was a bounded sequence, so my epsilon, in fact, let's see, when I did that, I had epsilon be the same epsilon. But now the simple fact would be xn times yn minus 0. That would be xn yn. And this yn, since it's a bounded sequence, that would be less than or equal to an m. And so if I would take my xn's to be less than epsilon over m. And so check. That would be less than epsilon. So that's a very easy thing to see just from the definitions. So an example that I showed you last time, I could have minus 1 to the n sine of n over n goes to 0. Oh, what's another easy thing? 2, if xn converges to something, then the absolute values converge. That's a no-brainer because of the basic triangle inequality. Let's see, I would have absolute xn minus eps. This is one of the triangle inequalities. That's less than or equal to xn minus x. And so if I make this less than epsilon, and of course the left-hand side is exactly what I want for the absolute values to converge. So that's a no-brainer. A more fun, easy thing, maybe. Let's suppose xn are non-negative numbers. Okay, so they're all positive. And xn converges to an x. Then it goes to infinity. Well, things that are positive, of course, would have to converge, or non-negative. There's no way those could converge to a negative number. I'll let you read in the book that. Then x, the limit, has to be bigger than or equal to 0. If it was negative, you'd come up with an epsilon that would screw things up, very simply. Draw the picture and think about it. So that's an easy fact. And the square root of xn converges to the square root of x. This is an important thing. Well, this is a fun thing to think about. We've sort of run into this multiple times already. Let's think about it. Xn minus yn, xn minus a square root of xn minus square root of x. This is kind of like the square root of n plus 1 minus square root of n thing. A classic trick is to multiply on the top and the bottom to make this a difference of squares. And when I multiply those difference of squares from the top, I get xn minus x, which I can make small. Okay, so now let me take the absolute values and get that. Absolute value of square root of xn minus square root of x equals xn minus x over, these are all not negative, plus square root of x. That would be less than or equal to x minus x over the square root of x. And I can make that less than it. Let's see, I could make this. So the aha is make xn minus x less than square root of x times epsilon, if n is bigger than or equal to n. And I would get the estimate I want. But this is another one of those oops moments. It is possible that the limit of xn's could be 0. And then I'd be dividing by 0 here. So it's one of those afterthoughts. This works great if x is not equal to 0. But oops, what if x equals 0? What if x equals 0? It's even easier if x is equal to 0. Then I don't have that square root of x there, and so I can mess around with square root of xn. I think I'll skip that for now, since I'm running out of time. This is an easy case. Think about it. So I should have split this up into cases. Do it first, and so you think about it. You can also find it in the book. I'll let you think about it. One thing I didn't mention that I wanted to is the squeeze theorem. So I'll suggest that you read